So tonight we're going to be starting Chapter 2. Chapter 2 is about reasoning and proof. So it's all about getting you to think logically through things. So the first thing we're going to talk about in 2.1 is inductive reasoning. Inductive reasoning is just reasoning based on patterns. So with inductive reasoning, you will be looking for different patterns to determine answers. Okay, and we're going to go ahead and show you an example of inductive reasoning, a few of them, and look at it. You've seen them before. A lot of times in inductive reasoning, we use sequences or geometric figures to discover different relationships. So let's go ahead and look at the first example. So here in number 1, we're asked to name the next two terms of the sequence. So what we need to find is a pattern in between these numbers. If we find a pattern, we can figure out what those next two will be. So here from 0 to 2, it looks like we add 2. The difference in 6 and 2 is 4, so we add 4 here. If we look on that, we add 6. So we're looking for relationships within these numbers. So you can see that we're going up by even numbers. So that means that the next term we will need to add 10. So after 8 comes 10. So 20 plus 10 is 30. So the next term in this sequence is 30. Okay? From there, we'll need to add 12. So the next term in our sequence is 30 plus 12, which is 42. Okay, so that is inductive reasoning. We're using patterns to come up with some kind of conclusion. All right, let's look at the next one. So we go from 4 to 1. So sometimes they can be multiplication, squares, division, different things like that. Here, I know that the difference in between these two numbers is a 3. So we subtracted 3 to get from 4 to 1. What about from 1 to negative 2? Well, there we're also subtracting 3. What about from 2 to negative 5? That's also minus 3. Okay, so we are just subtracting 3 from each term. So if we subtract 3 here, our next term here will be a negative 8. If we subtract 3 from negative 8, our next term there will be negative 11. Okay, so up here we were adding by evens. Here we're just subtracting every term by the same number. Okay, let's look at the last example on this page. So we go from 1 to 4. Well, a few things happen here. Either we could have added 4 or we could have multiplied by 4. Because 1 plus 4, oops, not added 4, that is so wrong. 1 times 4 is 4, right? So it looks like we multiplied by 4 there. From 4 to 16, 4 times 4 is 16. From 16 to 64, 16 times 4 is 64. So it looks like for each one of these terms, we're just multiplying by 4. So that means the next one will be 64 times 4, which is 256. So that is our next term. And then 256 times 4 is going to give you 1024. Okay, so those are using inductive reasonings to come up with some kind of pattern to figure out next terms. So let's go ahead and try this one. I want you to pause the video, come up with the next two terms here, and then when you unpause it, I'll have those answers for you. Okay, so there are the answers to those two problems. If you noticed in the first one, we're adding even numbers. We actually started with 6, then 8, and so on. So here we knew that the next term was 54 because we needed to add 14. We knew that the next term here was 70 because we needed to add 16. On that bottom one, this one might not have been quite as obvious. We're multiplying by 1/2 for each term. So 1/2 times 1/2 is 1/4. Excuse the bell. And so on. So if we do 1/8 times 1/2, we get 1/16, and 1/16 times 1/2, we get 1/32. Okay, moving on. So next we're going to define a word, conjecture. Conjecture is just a conclusion reached using inductive reasoning. So this is a conclusion reached using patterns. Okay, we see patterns, so we make a conclusion about a very broad subject. So for instance, let's look at this one. We want to make some conjectures here. So number 1 says the sum of 2 odd numbers. So I want to make a conjecture, a conclusion about the sum of 2 odd numbers. Well, let's just look at a few cases. So 1 and 3, those are odd. 1 plus 3 there is 4. Okay, let's see what else. 3 plus 5 is 8. Those are odd numbers. Let's see. 7 plus 9 is 16. And so on. So you can see, probably have already figured out a pattern already. 7 plus 11, it didn't say they had to be consecutive, is 18. So what do you notice about the sum of all these numbers here? Well, the only relationship that they all share is they're even. So we can make a conjecture that the sum of 2 odd numbers is always even. Okay, that is as specific as we can get, because other than that, they don't share any factors. Now let's look at number 2. Number 2 says the sum of the squares of 2 consecutive integers. Now this one may seem a little bit more complicated. So the sum, so we're adding things together, of the squares, so we're also squaring things, of 2 consecutive integers. So for instance, 3 and 4. Those are 2 consecutive integers. So let's see what that is. So that would be 9 plus 16. 9 plus 16 is 25. Let's look at another example. Let's do 5 squared plus 6 squared. So that would give you 25 plus 36, which is 61. All right, let's look at one more. I think I kind of see a pattern here, but let's try one more just in case. Let's do 4 squared plus 5 squared. Why not? So that is 16 plus 25. So that is 41. So the only thing I notice about all of these sums so far, and we could check a few more, we'd probably get the same thing, is that these are always odd. Now, if you thought about this a little while, that would make perfect sense that it would always be odd, because consecutive integers, it's always going to include an odd number. The square of an odd number is always odd. Okay, so it makes sense that the sum of the squares of 2 consecutive integers would be always odd. All right, let's look at this next one. We want to look at the sum of the first 30 positive integers. Okay, so I want to know now the sum of the first 30 positive integers, positive odd integers. Okay, so I've already started to make a chart here and just looked at each term, what the odd number was, what I was adding, and then the sum of those odd numbers. So the first term is 1, the sum of 1 is 1. The second term is 3, the sum of 1 and 3 is 4. The third term is 5, the sum of those is 9. The fourth term is 7, the sum of all those odds is 16. Do you notice a pattern yet? The fifth one, the number is 9. The sum of all of those is 25. We could go down and do the sixth one. The sixth one we would add in here would be 11. And if you added all of those up, that'd be 25 plus 11, that's 36. So do you see the pattern? Okay. The pattern of this is you take the number term and square it, and that gives you the sum. Okay, so if I wanted to know the 30th, the sum of the first 30 odd numbers, it would be 30 squared, so it would be 900. Okay, so we are making a conjecture and then finding an answer from that conjecture we made. And sure enough, if you were to add up those positive odd integers, you would get 900 as your sum. All right, so this is a try it, pause it, and then come back and you'll have the answer. Okay, so here are a few of the examples I tried for this one. Your numbers were probably different, but you should have come up with the same conclusion, and that is the product is always going to be odd. All right, the next thing we're going to look at is a counterexample. A counterexample is an example that proves a conjecture false. An example that proves a conjecture false. Okay, so say somebody makes a conjecture about something, but you instantly are like, wait, no, because this isn't so. So that's a counterexample. That's proving something false. So for instance, let's look at a few examples of those. I'm going to find a counterexample of this. The first question is, if n is prime, then n plus 1 is not prime. So we want to find something that proves that statement not true. So let's just look at a few prime numbers. We have 5. 5's prime. 5 plus 1 is 6. That's not prime. So that's not a counterexample. That won't work because it actually proves the statement true. So let's look at something else. What else? We have 11. 11 plus 1 is 12. That doesn't work either. There's actually, so far, I've only been able to come up with one example where this is true. And this will be the only example that will prove it false. And that is the prime number 2. Okay, 2 is a prime number. 2 plus 1 is 3. 3 is also a prime number. So this is a counterexample. It proves the original statement false. Okay? Let's look at the second one here. If angle 1 and 2 are supplementary, then angle 1 and 2 are a linear pair. So what this is basically saying is if two angles are supplementary, then they're always going to be a linear pair also. So let's see if we can think of a case where this would not be true. So with a linear pair, they have to be next to each other, if you remember that. So for instance, here's where 1 and 2 are a linear pair, but they're also supplementary here. So this doesn't prove it false. So that won't work. Okay? We need an example where it's going to disprove this. Well, let's look at this one. What if I were to draw an angle over here? Let's say this angle is about 30 degrees. Let's say it is 30 degrees exactly. What if I were to draw an angle over here that was 150? Well, if you were to add those two measures together, they add up to 180 degrees, right? 30 plus 50, 150 is 180. But they are not a linear pair because they are not adjacent. So this is a counterexample of the statement. Okay, it is an example of two angles that are supplementary but are not a linear pair. All right, so try this one on your own. This will be the last example of the night of the video. So pause it and then I'll give you the answer. Okay, so here is an example of a counterexample for this problem. You may have gotten a different one. As long as it proves it false, it is a counterexample. So the key here was using negative integers. Up here in the problem, it only said integers. It did not say they had to be positive, because the sum of any two positive integers will always be greater than the original numbers. But the sum of two negatives is going to be smaller, because we have that negative 1 plus negative 2 is negative 3. Negative 3 is smaller than both of those numbers. Okay? So come to class prepared, ready for questions, and we will be working on this the whole entire time.